let's review different types of electrochemical cells. So for our purposes, there are two types of electrochemical cells, the galvanic cell and the electrolytic cell, and they are opposite of each other. So they both perform the same function overall, but the electrons are going reverse from each other in the two types, and I'll explain what that means. In the first type, the galvanic cell, I'll show you an example here. Let's see. Here is the galvanic cell that we showed in class before we left. So here is the galvanic cell. Also called the Voltaic cell. And the key part is that it uses the chemical reaction drives electrical energy. By which I mean it produces electrical energy. And the key part of this is that the electrochemical reaction must be spontaneous. So what I mean by that is here, this example of the galvanic cell that we're showing over here, on the left side here, we are showing zinc metal going to zinc 2+. So if I write it up here, zinc on the right side here. So this is an oxidation. So this is the anode. On the right side here, I don't know if you can see it. Let's move over here. This reaction. I'll rewrite that as well. So over here, we have a solution of copper 2+, aqueous, and then we're adding electrons, and this becomes copper metal. So this is the cathode. This is a reduction. Oh no. Okay. We'll just go to blue. This is a reduction. So this is the cathode. And what happens is that when this reaction occurs on the left here, then electrons go this way, go here, and this way. So overall, this balanced reaction is zinc solid plus copper 2+ aqueous goes to zinc ions and copper metal. And then so what we're saying here is this is a galvanic cell. So overall, this reaction is spontaneous. And then so the electrons are flowing this way. So the reason that it's a galvanic cell we can do electrical work with it is if we then put a light bulb over here. So there's like a voltmeter here. So if we instead replace that voltmeter with a light bulb, then the electrons could drive this light bulb. So this is a galvanic cell. We're producing electrical work by running this particular chemical reaction. And so the key part is that we must have a spontaneous reaction for this to go. If we tried to do the reverse reaction here, if we wanted to go take copper metal and take zinc ions in solution, and then we tried to make a cell this way, this would not go because this is non-spontaneous. So overall, this is a galvanic cell. Now, the other type is the electrolytic cell. So that's over here. So electrolytic cell. So in this type of cell, we're using electrical energy, like a battery. Electrical energy to do chemistry. So in this particular example, we have here molten sodium chloride, oh dear. And then, so sodium chloride is very stable, it's a salt, but if we want to separate it out into its two components, so here we have the cathode. So this is reducing sodium ions to sodium metal. Oops, sodium 0. And then over here is the anode. Let's see if I can circle this. And then we have chloride ions, 2 chloride ions going to chlorine gas, plus 2 electrons. So this is the oxidation, this is the reduction, and then the way we can get out sodium and chlorine gas would be to use this battery. So if you were to hook up a car battery to molten sodium, you could generate chlorine gas and sodium metal, 2 bad things that you don't want to happen, probably in your dorm basement, which actually happened. I think I told that story in class. So that's why this is the reverse. Here, we're using a battery to do this chemistry, and here this chemistry goes, and we can use it like a battery, basically. So that's the difference between the 2 types of cells. And then the last thing I want to talk about is to do cell notation. So obviously, we can do lots of chemical reactions. We've balanced many different types of electrochemical equations and redox reactions. So we can use these as all different types of cells, but drawing this whole picture or this whole picture every time is rather inconvenient. So there's got to be a better way. And so this is the shorthand notation for electrochemical cells. And that's called the cell notation. Cell notation. So again, by convention, what we do is on the left side, we draw, I'll proceed. Okay, on the left side, we'll write the anode reaction. So this is the oxidation reaction. Now on the right side, we'll write the cathodic reaction. And then from there, we can then write the balanced electrochemical cell. So for this galvanic cell that we just talked about, the anodic reaction is the oxidation of zinc metal to zinc ions. So we can write that equation out. Instead, we don't need an equation this time. We can just write the 2 different components. So zinc, solid, is getting oxidized to aqueous zinc ions. And then the cathodic reaction, we were saying that copper 2 plus ions were getting reduced to copper metal. And so the part that some people were confused about last time was the concept of phase boundary. So a phase boundary is when you have 2 different phases of matter that are going on. So in this case, we have a solid zinc electrode and an aqueous zinc ions. Same here, we have a solid copper electrode and aqueous. So we have liquid to solid phases. So then we just, by convention, write out this phase boundary as a line. And then finally, we have the so-called salt bridge, which was also present in the other galvanic cell that we showed. That's the tube of ions, like potassium chloride. And the reason we need the salt bridge is because, for example, in this particular reaction, as this reaction proceeds and we generate electrons, we're removing copper 2 plus positively charged ions from solution as we deposit copper metal. During this process, then, we would eventually be building up a lot of negative charge, right? Because if we're losing cations, we still have anions in this beaker, then we don't want to build up a lot of negative charge. So the salt bridge balances that out by having more cations come over, like potassium. In the meantime, anions are coming over here to balance out the loss of, as we accumulate positively charged zinc, the solution gets more positive. So if we didn't have this salt bridge, the reaction would eventually stop because we would have no more driving force. This is a concept that we'll get into a little bit later as well. So overall, this is our final equation. One thing that we mentioned at the end of last class was also the concept of inert electrodes. In this example with zinc and copper, the electrons are being conducted by the zinc rod and the copper rod that are connected by a wire. And then so the zinc rod serves to conduct electrons between the beaker and the wire, but it also participates in the reaction. But we could have electrodes that conduct electrons and do not participate. So examples that I mentioned in class last time were platinum, a very common kind, maybe gold. and also maybe carbon, so graphite, for example. So the key point is they do not react, but transfer electrons. So they got to be conductive. So an example that we ended up class using was the concept that if we want to think about that iodine oxidation by permanganate, we have this electrochemical cell. We have I minus aqueous going to solid I2. And so it's not convenient to make a whole electrode out of iodine. It's not a very nice solid. It's also not very conductive. So what we can do is, if we have both of these in a mixture in a beaker, we can also put in a solid graphite rod. So this will be our carbon electrode. And so this carbon electrode, again, there's a phase boundary here, will be connected by a wire to our second part of the cell, and then this will just conduct electrons to our iodide, or from our iodide rather, and then that'll connect it over to the other beaker. But the carbon itself is not oxidized or reduced. And then on the other side, if we want to have the acidic permanganate oxidation, we could then have permanganate. And again, here there's no phase boundary because permanganate and the manganese 2+ ion are both aqueous. Oh, and then here we'll also include protons because they will be there in the balanced final equation. And then we'll again conduct all of these electrons from here over to here through a carbon electrode. And then so in our actual cell, if we were to draw this, we would show like these two electrodes would be connected by a wire, and then so our electrons are going here, so electrons going this way from the iodide to the permanganate, and that would be our cell with inert electrodes. So this is how you show that we can convey all this information, cell bridge, phase boundaries, types of inert electrodes through this cell notation. Okay, thank you.